Hello everybody, welcome to UNS EduTech's science concept videos. In this session, we are going to discuss about an important concept called electromagnetic induction, and there are two laws associated with that. One is Faraday's law of electromagnetic induction and Lenz's law. So before going to the details of the law, I will take you to a small experiment so that you will exactly understand that what exactly is electromagnetic induction. Here, in order to show that, there is a galvanometer. Galvanometer is a device which can sense very feeble current. Even if the current is in microamps, we can find out that current. Now, this galvanometer is connected to a copper coil having very low resistance, and here I have a magnet. You know that magnetism is a fundamental property, and because of this electron spin around the atoms, magnetism is generated. And if you have a magnet, there will be a region of space around that magnet where its force is experienced. Now, I am going to do one thing. Here you can see this magnet I am going to insert into this coil. So, if I am inserting this magnet into the coil, you know that the field around this magnet will be touching with or is in contact with the coil, and inside the coil you know that there are a lot of conduction electrons are there. Now, look at the galvanometer reading. You can see that here if I move this, galvanometer is showing some deflection. So, this means that when there is a relative motion between the magnet or the magnetic field and the electrons, you are getting some deflection or a current is generated, an electric current, a flow of electron is generated. So, this phenomenon is called electromagnetic induction. Here actually what happening is, here you know that this magnetic field is moving, the magnetic field, when it is relative, there is relative motion between the electrons or the conductor and magnetic field, the electrons will experience a force, and if the circuit is completed by connecting the ends through a load or through a meter or through any device, current will flow in a loop form. So, as a result you can experience a current or voltage is experienced or e.m.f is experienced across the conductor ends. E.m.f is actually a misnomer, is actually electromotive force, but dimensionally that quantity is nothing but voltage or potential difference across the conductor. Okay. Now, let me take you to another experiment. Here again I have a not a galvanometer, I have a voltmeter here, again connected to another coil, and I have a magnet here. This is a high quality, high power magnet. This is NdFeB, neodymium magnet, is way more powerful than traditional Alnico magnet. Here you can see that when I try to move this inside this coil, see, you can see that this glowing, LED is glowing. So, here this light is glowing because the current is flowing through the LED, and here you can note down one interesting thing. See, if I am moving very slowly, you can see that there is no glow, the LED is not at all glowing, but the more faster, if I am moving it faster, you can see that it is glowing brighter. The more faster I do, the light become brighter. So, here when Michael Faraday did this experiment first time in 1831, he tried to observe what are the factors influencing the quantity of e.m.f generated or the voltage generated. Now, here you can see that here when I am moving faster, that is one of the important quantity, that is nothing but when I am moving this, the magnetic field associated with the coil is changing, it is changing with respect to time. If I am moving faster, the time is very small, so that change in, or if I am taking the magnetic field by change in time, that quantity will be a very high quantity. So, more voltage will be generated. Apart from that, the number of turns matters. The more the number of turns, more e.m.f is generated, and more the area of cross section, more e.m.f is generated. See, let us go to the mathematical aspects, then you will understand what exactly is Faraday's law of electromagnetic induction. When Michael Faraday originally did this experiment in 1831, he observed that induced e.m.f is proportional to the number of turns. Okay. Then E proportional to area of cross section. Then one more important quantity, it is dependent on the rate at which the magnetic field is changing. So, we can see that E is proportional to delta B divided by delta T. Delta is representing a small change. Okay. So, the magnetic field is represented by a letter B. So, delta B by delta T is also dependent. If you are moving very fast, the time will be very small, this quantity will be very small. In the denominator, if it is a small value, that this quantity will go up. Now, if we combine all this proportionality together, we can write down that E proportional to N into A into delta B divided by delta T. Okay, delta T, delta is a Greek letter which represents a small change. Now, this we can equate, E will be equal to NA into delta B divided by delta T. Okay, this is a single quantity. Now, we can see that in SI unit, if you are putting all values in SI unit, the proportionality constant will be 1. That is why we are not mentioning that. Now, one more thing, see, if you are multiplying, there is another important quantity in electromagnetic induction, that is nothing but flux. Magnetic flux phi is nothing but the product of magnetic field and area of cross section. If you do that, you will get phi is equal to BA. Now, if I am replacing that here, you will get N into A into B delta B, you will get delta phi. So, we can replace that equation like this. You can see then EMF induced will be equal to N into, see, delta phi divided by delta T we can write down. So, this particular law is called Faraday's law of electromagnetic induction. This will give you a quantitative value for the EMF induced or the potential generated across that conductor. Now, let us go back to our first experiment once again. Here, you can see that you might have noticed in the first time itself, if I am moving here, you can see this is a north pole. Using a small dot, we can see this is north pole, this is south pole of this magnet. Now, if I am inserting this magnet, I am lifting this magnet, you look at the needle. You can see that if I am lifting, it is going towards right side. If I am inserting, it is going towards left side. So, this is very important concept. See, first of all, you have to understand that this system is not a source of energy. This is only a device which we can convert the mechanical energy into electrical energy. When you are moving, you are applying certain amount of energy on the system and the system will produce certain amount of energy. Now, this phenomenon we can explain with the help of conservation of energy. We can say that it is consequence of conservation of energy. Now, let us see how it is happening. Here, when you are moving this magnet, you can see that there is a magnetic here this magnetic field is cutting the conductor, and we can say an EMF is induced in the system. That EMF, that whenever a current is passing in a coil, that EMF will generate another magnetic field. That magnetic field will try to oppose, and we will experience a difficulty in moving whatever motion you are attempting. For example, when you are trying to move north pole into the system, the induced current direction will be in such a way that this end of the coil become north and it will try to repel or resist the motion. So, if you are moving away from that, the direction of the current induced will be in such a way that it will try to become a south pole, so that it will arrest the motion by attracting the magnet. This phenomenon or this law, this is actually a qualitative law. This is comprised in the form of Lenz's law. So, Lenz's law can be quantitatively simply expressed by putting a negative sign in this equation. You can see the Faraday's law of electromagnetic induction is E will be equal to number of turns into change in flux with respect to time, or number of turns into area into change in magnetic field with respect to time. If I am putting a negative sign here, this will incorporate the Lenz's law into this equation. So, this is showing that the induced EMF or the variation of EMF and the flux will be in opposite direction. That is idea. This is a consequence of conservation of energy. Now, let us visit a schematic animation of this phenomenon. Here you can see there is a magnet, north pole and south pole, and I can show you the magnetic field lines. See, here this coil is connected to a bulb. Now, you know that same as what we did in the experiment. If I am moving this, you can see an EMF is generated and the bulb is glowing, a current is flowing in the circuit. Now, we can see that if I am moving very slowly, the brightness of the bulb is very less, and if I am moving very fast, you are getting very good brightness. That shows that Faraday's first law or Faraday's law of induction, electromagnetic induction. The rate at which the magnet is moving will reflect in the brightness or the amount of current generated, amount of voltage generated. Now, if I connect a voltmeter, you can see the Lenz's law. Look at this. If I am pushing the north pole into the system, we can see here the deflection was towards left side. If I am taking out, you can see the deflection was towards right side. This shows that Lenz's law. Here I told you this device is actually not a source of energy. You know that battery, if you are considering battery, that device is a source of energy. Here this device will convert the mechanical energy into electrical energy. So here the conservation of energy is applicable. Here when you are trying to push this north pole into the coil, that side, you know, the current generated will be in such a way that current will be making another magnetic field, because whenever there is a current flow in a circuit, there will be a magnetic field around that. So here induced magnetic field will try to oppose this north pole so that the motion will be opposed. So we are doing work against that opposition. So here you can say the direction will be in such a way that this side become north pole and try to repel the system. In the same way, if I try to remove this north pole from that location, the current direction will change and the that side become a south pole when you are moving away. So that south pole will try to attract that magnet. So this is why we call it the direction of the current will be always opposite to the change of flux. So this is called Lenz's law. So both Lenz's law and first Faraday's law of electromagnetic induction we discussed, or we shown through schematic animation. So we discussed about electromagnetic induction and two important laws associated with that. First one is Faraday's law of electromagnetic induction, which will give you a quantitative estimate for the amount of voltage induced, and then Lenz's law, which will give you a qualitative idea about the direction of induced EMF. I hope all of you understood these concepts thoroughly. Now, do you wish to learn science like this through experiments, animations, simulations, and followed by mathematical explanations, so that you will be thorough with your concepts and sharp in your analytical capabilities? If you want to know more about the details of UNS EduTech and the courses offered by UNS EduTech, you can contact our counselors through the numbers given at the end of this video, and you can talk to them. You will get more information. So thank you very much for watching this video. You can subscribe to our channel so that you can get the updates. We'll come up with a new video soon. Thank you very much. See you with the next video.